page, and I've written a kind of what I think is a kind of unique collection of activities for algebra. Activities designed to make algebra learning more active and engaging and to connect ideas that otherwise don't seem to get connected for students. And so today I'm giving a talk called Algebra is Weightlifting for the Brain. This is kind of interesting because usually I give the technology talks. I watched Rochelle give the technology talk. And I'm not talking about hardly any technology in this, which is really odd for me. But I hope you'll bear with my little story here. There we go. So this is actually a talk that has 3 storylines to it, and I hope they interweave together somewhat seamlessly. I guess we'll see how it turns out. I want to tell you a little bit about my story and how I came to write this resource and how the thinking that went into it. I want to talk to you about the problems of algebra, because I think we have some significant problems in algebra, and the creation of what is this classroom resource that I hope gets used in as many places as possible, because the goal of writing it was to get it out there into classrooms, and that was it. And so the binder that you see a couple people in this room have managed to snag copies of is a free resource given away to people who adopt a multitude of textbook lines. So I hope that you'll understand what went into it and the philosophy behind it and why you might want to use it. So I want to start where I started, and this is actually me about 5 years old. And I have really honestly been thinking about how to teach math for about 30 years. When I was 5 years old, my mother had a stroke. She had a math degree. She lost everything. So she completely lost her memory of everything she'd learned, her ability to talk, her ability to write, her ability to do math. So from the age of 5, I found myself teaching math and teaching all sorts of other skills. And not only that, but teaching it to somebody whose brain was a little bit miswired after that point. And so I really have literally been teaching math for about 30 years and been thinking about how the brain works for about 30 years. So I had a significant edge. When I got to college, when I started teaching in graduate school, I had a significant edge because it was not my first time thinking about teaching. If you've ever tried to teach somebody with a significant brain injury, you know that you have to try 30 different things, and on the 31st, for some reason, that works. So for everything I had to teach her, I had to think of 30 different ways to do it, and it gave me a lot of flexibility in how I taught. I want to actually start this talk by talking about the many problems that we face in algebra, and I just actually want to get some of your thoughts on what you think the problems we face in algebra are. So let's hear it.
Students don't like it.
Students don't like it.
Doesn't seem relevant.
It doesn't seem relevant?
They think they have such thing as math anxiety.
Yeah. Math anxiety, believe it or not, they think it's an issue, okay?
They want an algorithm for everything.
They want an algorithm for everything, absolutely.
They really prefer us to do a Vulcan mind meld. So they don't have to do any work.
They want the direct download of algebra,
Yeah,
right? Instead of the learning process of algebra,
Right.
okay.
Yeah,
What
so
else?
when we use this, where are we going to use this? They want a list of every profession that needs it.
Where are we going to use this? Okay. What else? What other problems do we face? Think bigger. Not just with students. Who teaches algebra? I mean, how many of you have, like, the majority of your classes taught by adjuncts? How much warning do they get?
3 days or 4 days.
3 or 4 days, right? And there they go. They're in the classroom, they're teaching. Some of them for the very first time, right? I would say that's a pretty significant problem. Any other problems? It's your time to get them off your chest.
Training for grade school teachers.
Training for grade school teachers, okay?
I think in some classes, the heterogeneous as opposed to homogeneous, if they get to self-select as opposed to happen to test into a class, you have
So
such a
skill
wide
levels,
range.
variety of skill levels in the class. I think that's a big issue. You have everything from the student who's taken algebra a couple times and is just brushing up to the student who like has never seen it before in their life, and those two personalities really clash in the classroom. You think? All right. So I'm going to go through 4 of the problems that as I see them, and I'm going to start with problem number 1, which is that student conceptions of math are really fragmented. And what this means is that students see math as a collection of formulas. If I can just memorize enough formulas, I will pass math. Do you see that? They don't see it as a cohesive body of knowledge that all interconnects and has deeper meanings. It connects to real-world applications. There's actually a test you can do on students' conceptions of math, and it's a continuum from fragmented to cohesive. And I would say that especially at the lower levels, what we see is that students' conceptions of math are very fragmented. The problem with that is that when students' conceptions of a topic are fragmented, they tend to learn at only a surface level. They focus on things like memorizing. If I can just memorize the algorithms, I'll be okay. Or if I can just memorize the formulas, I'll be okay. And we know that that's not the case. It's not the memorization of the formulas that's the problem. It's the knowing when to apply which procedures and knowing, that this problem is different from this problem and activating different procedures, being able to connect those to the real world, to more subjects. So unfortunately, our students are stuck here in this kind of surface level learning. So, as I began teaching algebra many years ago and at all sorts of different schools and all sorts of different settings, having spent all this time already thinking about learning, I started reading everything I could about cognitive theory, about how the brain learns, about how students learn, about math. And so I did a lot of reading, and we're actually going to start here by doing a little side course. We need to get to know the brain a little bit better so we can understand what's going on so we can tweak it. Okay? And so we're going to do a little side course, short side course in cognitive theory as it applies just to learning algebra. Okay? So the first thing I want to teach you about is called a schema. It's a mental representation of what all instances of something have in common. Okay? So as we go through and we learn problems, we form in our minds these kind of packets that tell us, okay, all of these things, they have this in common, and all of these things have this in common. So for example, if you look at possible schemata for factoring, they might look something like this. A GCF, we take the factor in front, it's got a set of parentheses, right? Trinomial factors, you see students do this all the time, right? They start by making the parentheses, right? That's what their schemata, that's what their schema tells them to do. When you solve something with an equals 0, you put x equals, right? Of course, one problem is that this one looks a lot like this one in their minds, right? And so after they learn this one, they apply it to that one. You see it all the time, right? You might have one for grouping, which is 4 terms, 2 groups, something like that. They have some mental image of what that looks like. Okay, so that's the formation of what are called schemata. Sometimes we call these schemata like scripts. They're little mini scripts that run. Okay, we form these all the time, not just in math. You have a little script that runs that tells you to get from home to school, right? And sometimes that runs even when you didn't mean to get to school because you make that trip so many times that you meant to go to the bank and you end up at school instead. Your mind is just running that procedure, and it does it on autopilot, essentially, once they're solid. So these schemata, they help us to categorize the experiences we have. They help us to remember and comprehend what we experience. So the more we have, the more flexible they are, the better we are at processing information. And, of course, developing these is really important to problem solving. If you have a student who only has this one developed and none of the rest, how are they going to do in factoring? Not great. And if instead they take this, they have this as you go through the first section, right? Then you go through the second section and all they do is replace this one, not create a new one, but just replace this one. They go to the third section, they replace this one. If they keep doing that, if they keep just replacing the existing schema, then there's a problem there. We need them to actually formulate all of the different ones as they go, not just replace, 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 replace. If you've ever had a student who seems to follow you, like they follow you in class every day, and then they get to the test at the end of the chapter, and they seem to have lost everything. That's what they're doing. They're just replacing the schema they have with the next one. They're not seeing that they're two different things that need to be stored. And so we need to work with them on getting those different stored. So I want to walk you through an example with math just so you can kind of see how this works. So we're going to look at a factoring problem. Factoring is a great example of the formation of these. So here's the story. I've taught factoring. I went through all the different GCF, grouping, trinomials. I've gone through this type of problem already. I walk into class the next day, and as a review, I put this up on the board and I say, okay, go ahead, give this one a try. Okay? And so here's what happens. Many students do this. Have you seen this? All right? What happens here is that they run the wrong script. They say, okay, I'm going to make 4, right? So they've made 4, not even very well, but they've made 4. They've made the -5 very well. They haven't quite perfected the 4, and they've completely missed the 6. Right? So they basically run a faulty script. The problem says factor, and they said squared term in front, check. 3 terms, check. Run trinomial factoring script. And they've got one script in their head, and they ran the one they knew. Okay? So I think to myself, okay, well, I don't want to give it away. Let me give them a hint and see if that helps. So I give them a hint. Oh, it's important that we look at the first number and the last number here. So we give them a hint. So maybe something like that. Okay? And so here's what I get next. You seen this? I'm hoping this feels like a familiar storyline to you. Okay? It's a story you've read to your class many, many times, like Goodnight Moon or something, right? So here we have, they've successfully found a pair that makes -5, and they've stuck them into the trinomial script that they have in their head, right? Again, missing the point that the last number or the first number, there's other things that happen here, okay? So the students still ran that trinomial factoring script. They still don't have the right script that they're pulling up. And so if we back up a little bit, I gave them one more clue. Okay, I write out the series of terms for them. And at this point, the right script runs. They go, oh, grouping, that's a script I know. 4 terms, I know what to do with that, right? I underline a couple terms, and I run the factoring by grouping script, and now I'm to the correct answer. But you see that along the way, there were all sorts of opportunities to run the wrong script. So, why did the students struggle so much with that?
They want to get to an answer immediately.
They want to get to an answer, right? That's the most important thing. And what seems to be the strongest script in their mind?
The one coefficient.
The one coefficient script, right? The 2 parentheses script. And they're just diving in. As soon as they see that that's a possibility, they're just diving into it. And so really what we need is, we need another schema here. We need something that runs in their head when they see that there's a number in front. And we need that, we very much need, and this is important, we very much need for this script to look different in their head than that one. Because if it doesn't, we tend to store these schemata with visual images, not text, visual images. And so if we don't recall a visual memory that's different, then we won't run something different. And that's really important, because algebra is so much text. But when we remember stuff like this, we remember images. And if you think about how humans have developed, language has only been a recent technological development. Written language is only a recent technological development. And written language for the masses is even more narrow. It's only been maybe 400 years since we had printed materials that were readily accessible, maybe, to most people. So for tens of thousands of years, we communicated by audio and by visual. We trained our brains to remember how to do things by an image, not text. Okay? So we have to make sure that we give students some kind of visual cue that helps them to trigger these different things. Okay, so successful problem solvers tend to have a large variety of these flexible schemata. Not just one, but many. And they are able to access them all. Unfortunately, we've seen this too. Math students, they make one, and then they try to, it's the hammer thing, right? Give me a nail and I'll hammer it. I don't remember how that saying goes now, I've completely blanked it. But there's a saying here, right? Anyone remember the saying that I'm trying to come up with here about the nail and the hammer?
You have a hammer, everything's a nail.
If you have a hammer, everything's a nail. Thank you very much. That's exactly what I was looking for. So, for example, there's this distribution schema. Our students, I think, are born with it. I think it's there at birth, basically. And it's this idea that you can distribute the same thing to everything, right? It's a very, very, very strong schema. It's that schema, right? What happens when I give them this?
Distribute.
Or that?
Yeah.
Or that? Do you see it? They have made a very strong intuition for how distribution works. And once they have that hammer, everything's a nail. Okay? Here's another one. Yeah? Right? Once you have the hammer, everything's a nail. And so the important thing is that somehow we have to get them to store these problems in a different way than that. They have to see that there's a difference there, that they have to activate a different script when they see it. And I don't think that we do a good enough job because we kind of march through material, in a textbook. We very rarely get the opportunity to come back. I mean, how many of you after teaching this have been able to incorporate this right into the lesson as you go to make sure that those old scripts aren't being rewritten, right? Because you might teach this first, but as soon as they learn this, they overwrite this script. You didn't mean for them to do that, but they do it. Okay, so again, we need to realize that these schemata, they are being stored with images, and probably that image right there is very, very strong. And we reinforce it all the time, and that's not our fault. It's the easiest way to show it. We have to be very careful about how we do it. So I want you to just spend a couple minutes and see, I've given you some for factoring and distribution. I want you to think with your table about lines, about what happens when you learn to graph lines, find the equation for lines, and see if you can think of some visual images that students might store and some of the very strong scripts that they run, right or wrong. Okay? I'll give you a couple minutes to do that.
I'm going to hand it out towards the end. So there is a handout.
Supposed to come up with
About mine. I know, like the slope intercept form, I always try to reinforce that B is an ordered pair, that the intercept is at 0 and B. Because
they always want to just write the B.
Just write the B, and then when you get to when you graph y-intercepts, you might get an x-intercept of 0, 2, and a y-intercept of negative 2, 0. But they graph 2, negative 2.
Right.
Which is like, I don't understand that thinking. But it seems to go back to reinforcing, and I don't know how to, it's got to fit in here somehow that, to think of ordered pairs as ordered pairs.
You guys come up with some? I'm going to ask you to share maybe one or two. So,
How would we write that as a
You guys do it for them.
think about how to say this, how the way to say it.
I want to make that as an order. I was just going to do the B part.
Or x-intercept 0, say x1. Y-intercept 0. I graph okay, we'll say something like that.
It's like, yeah, whatever you guys say.
Processes is what you guys are talking about.
I'm sure you could think of someone in English. Oh, I should pause this.
Showing all different things on the board that this is slope is defined as all the
How do you pause this, Maria?
you just actually hit stop and then start another one. It's fine. If it's multiple videos, it's fine.
Okay.
All right, let's hear back from the groups here and see if you came up with any strong schemata that you see from students. So I'm going to start with Jill's group here. What did you guys come up with?
We came up with x and y intercepts where reinforcing that those are ordered pairs. Like they come up with an x-intercept of x0 and a y-intercept of 0y, but what do they graph? XY.
Yeah. Oh, that's a great one, right? I mean, they say, you know, like x equals 5, that's the x-intercept. Y equals 10, that's the y-intercept. So what's the point they graph? 5, 10, right? Not intercepts, but a new ordered pair. So they have a very strong idea that those have to be put together, right? Okay, what'd you guys come up with?
Well, we kind of talked about slope, how it's often taught rise over run. And so when they get a negative slope, a lot of times they ignore the negative sign. They still want to go up and over. And so they'll end up with it, you know, being the opposite of what the slope truly is.
Right.
But they'll just forget about the negative sign, or, you know, other times they keep thinking rise over run. If they have a y-intercept, say that they have a piece of 6x6 graph paper, and they have a y-intercept that say 0, 5, and a slope of 3 over 2. I said, well, I can't do it. It goes off the paper. Every time you see the graph,
Right.
I draw the wrong line.
Right. I think mentally, probably the image of slope is an upward rising line with a slope triangle, never a downward triangle. And so we have to figure out ways to tweak that, to get the kid to be stored in alternate ways. Okay, how about you guys?
We mainly were talking about the same thing, I believe, in that they want to hammer everything into y equals x plus b when they're writing the equation of the line, rather than paying attention whether they have a y-intercept or not. And then the other thing, as they were talking, I thought of is we usually do the line chapter right after we've solved. So when we ask them to find the x-intercept and the y-intercept, they write x equals 3, y equals 5 when they think they're done. The sad thing is sometimes the back of the book even has that, as opposed to having them as points.
Right.
So they really think they're looking for a solution and not looking for an ordered pair.
Right.
Right.
And you guys?
We came with two problems with lines. Judy has a problem with students getting locked into the y equals mx plus b, and they don't really know what they're doing. And I get students who come in that have been taught in high school to find the b. If they have the m and the y and the x, I can just put them into that and somehow magically get the b.
Right.
But if you teach them the point slope form, I'm just going to say it's so rote that they don't have any idea what they're doing with the point slope form.
They don't see that both methods find the same thing.
Right.
It's very difficult for students. There's one other that I thought about that I haven't heard here, which is that I'm going to not pick on these guys because they're just sending me notes, 5 pieces of paper. But that's, vertical and horizontal lines. I mean, they just don't have the concept, right? You give them x equals 3, they plot 3, and they make a horizontal line at 3, right? Or they make a horizontal line at the y equals 3. They see x as being horizontal movement, so x equals 3 must be a horizontal line. They're not catching that x equals 3 means the x coordinate's always 3. So I think we have some barriers to overcome here. They're hardwired for some of these beliefs. They're very natural. You have a hammer, all the wheels a nail. It's the best expression for this. I think you have to keep that in mind. Okay, so what we really need students to do is practice recognizing these differences, right, and categorizing what they see into the proper places. We need to bring students all of the schemata they already have in their heads, whether we made them or not. We need to bring them up against situations that really challenge them. And we needed to do it in class. We needed to do it where we have the best point in time to influence them. Because when they do it at home, they see it in homework, it's just a frustration. I got this, the book got this, grr. It's not the same. They don't make the connections necessarily for why it's different. So what we can do in the classroom is we have this very valuable time where if students are able to butt up against these schemata on their own in class, we can actually serve a very important purpose as teachers there, and that is to help them to see the differences and try to help them start to build those new schemata. There are 3 processes here that brain goes through as we bring their schemata into situations that refine them. We go through a process, we try to bring them into a process where they do abstraction, just abstraction and interpretation. And all of these words are on the handout I will give you at the end. And this presentation, I should mention again, is on the internet, so you can watch the whole thing if you'd like. So, if we can encounter objects in new ways, then we can revise and refine these things. Not just stamp a new one on top of it, maybe make new ones, make tweaks to the ones we have. So you remember this problem we were looking at, the factoring problem. I wanted to change the approach to this kind of, as a review, what could I put in this problem instead that would get students to recognize that they can't just run that one script. And so I changed it to this. I put up 2 problems instead. Now you can't help but notice now that there's only one difference between the 2 problems, right? And that's the 6. And so, they tend to have this script that, well, if the problems are different, then the answers are probably different, or at least the methods are different, right? They have that script from birth, pretty much, too. Different problems, different answers, okay? Which is, not 100% true all the time, but, most of the time it is. So, different problems, different answers. And so what I want them to do now is look at them carefully and go, okay, well, what is the difference? And maybe then recall that there was a different script for this and get some more practice running it. Okay, so this one, then they might run with that script that I visualized as being, connecting the 6 and 4 and then doing the group terms. And this one, they might run with the 2 sets of parentheses, if that's the way they're starting to store their information. Okay, so we need to have multiple encounters with objects in different ways. And different ways is very important. We're not talking about repetition here, okay? Repetition is, like what we do with the gym, and what we do when we're trying to learn an instrument. And we do it to some extent when we're trying to learn one new process. But that's not what I'm talking about here. I'm talking about being able to separate processes. Okay, so this is an example of repetition with algebra. Okay? You're always running the same script for this, right? You're factoring, and you're always using which script? Difference of squares, okay? So that's just repetition, rote repetition. Now this would be a refining of that one schema, okay? That one script. And it refines it how? What does this one do?
It doesn't factor.
It doesn't factor. So if they've got the idea that anything with squares will factor with difference of squares, this breaks it, right? So we're refining the one that's already there. This one, how is this different? There's a coefficient there, right? It's not just W and W in the first part, it's 2W and 2W. So you've got to refine again. This one's a refinement in the second term. So while this is still all running the exact same script, we're now refining that script and trying to make it a little bit more robust. Okay? A prettier hammer, so to speak. Okay? But now this is where I think we really need to go, and this is abstraction. So we're no longer talking about one script, we're talking about multiple scripts, and we're asking students to decide which scripts to run where. Right? The reason that these problems all look alike is because it forces students to look at the very fine detail on the problem and learn that that little fine detail is really important in math, right? It's all the difference in the world between running a difference of squares script and a sum of cubes script. Okay? So we need more of this kind of work. And again, I think the place that we need this kind of work is inside the classroom, where we have the opportunity to step in and say, when they're so sure that they factored this as x plus 8, x minus 8, we have the opportunity to step in and go, maybe you ought to multiply that out. The back of the book won't do that, but we can do that when we're there in person. Okay, there's another process going on here, and it's called gist extraction. And what it does is it revises what you actually experienced in order to store the memory. Probably you can't remember everything you did yesterday, right? You have kind of a gist of what happened, the main points of the presentations you went to, okay? So you basically revise the experience you have, and then you store that memory. So I wanted to show you what happens when students go through this. So I'm going to show you an example of one way that many instructors, I did it at first, and probably some of you do it, and many of our adjuncts do it this way, because this is the way most of the textbooks teach it, okay? So I don't do it this way now, but we're just going to use our imaginations, okay? So this is very standard. We're learning to multiply polynomials. We've already gone through multiplying by a monomial. Now we're talking about multiplying two binomials, right? And so we kind of show them this. There's that nice distribution mean that we've got going, right? And we show them FOIL. Okay, so FOIL, you might get multicolored, very nicely laid out. The best job you can possibly do of it. And then you show them a few more problems, and you work your way up to the harder problems of binomial times a trinomial, and all of that's great. So what do you think students remember when they leave class? Foil. One word, right? Foil. They remember that, right? And so the gist of the class is that if you have to multiply by polynomials, use FOIL, right? If they're going to boil it down to one thing, that's what they're going to remember. And even worse than that, in addition to the gist extraction, that is the melting pot of ideas, there is this thing called interpretation. You didn't say it, but they got it, right? They interpreted it. We all walk away from every situation that we experience with our own interpretation of what happened. It's how you can take two people who were in the same room and get a completely different understanding of what happened in that room. So there's their interpretation. You didn't mean for it to happen, but it did. Okay? So interpretation is basically filling in things that were not said or seen, but they happened anyways. So for example, here's a very common one that we see interpreted. You teach them how to multiply exponents with like bases, and then right after that, they do this. You did not teach that to them, right? But they took this, and they took an older situation that they had, and they just overwrote it, right? They said, oh, this, I can apply it there, right? That nicely developed schema that you had just got killed by the new one you taught them, okay? So now that we know about that, we should change the tactics of how we would teach that particular type of factoring, okay? And so here's one possible way we can do it. And this is the way I would do it now. If I'm not using manipulatives or something like that, I would probably use that too. But as a better structure for this, knowing that they're going to walk away with one main idea here, I start with this problem instead. I do not start with binomial times a binomial. Because in this problem, what I can show them is that every term here multiplies by every term here. And we can line them up, get nice lines of terms, adding like terms, things like that. We move on from that to a trinomial times a trinomial, which follows the exact same procedure, every term in the first times every term in the second. Okay? And so what I'm trying to set up here is not FOIL. I'm trying to set up, when you multiply polynomials, take every term of the first, multiply it by every term of the second. Right? Eventually we get to a binomial times a binomial, which by now is like so piece of cake. I don't need to talk about FOIL, because FOIL is naturally what happens when you multiply every term of the first by every term of the second. Of course, some poor student in the class always tries to mention FOIL. Oh, you can use FOIL for this. Right, and then you have to have a conversation about that. But what I'm hoping is that by doing it in this way, when they leave class, by never mentioning the word FOIL, that is not the strong thing that sticks in their mind. What they remember is the multiple arcs going across, and the multiple arcs going across. And that's the mental image that they come out with, instead of FOIL as their mental image at the end. Okay. So as visual cues, again, I think the multiple arcs are probably what they're doing. You have to start thinking about the fact that there are visual cues for everything that we teach, and that's what's sticking. Okay? Okay, so thinking along these lines, I was frustrated with what I was seeing come out of students, and I started writing activities for the classroom. Just on my own, I thought, this stuff needs to happen in class. I need to correct these things in class. I need to write activities that help them bash these ideas up against each other and really start looking at what's going on there. So I started writing activities, and I'm just going to show you a few of them. So this is an activity that tries to help them see that like terms is always what we're talking about with addition. So this is an activity I use when we start talking about roots. So we start with 3x squared plus 5x squared. They're good at that. 3 11s plus 5 11s. Also a like terms problem, right? Then we go on to square roots. Now this is before I taught them anything about adding like terms, but they see the pattern. They go, okay, if this is 8x squared and this is 8 11ths, then this must be 8 square root of x. But by the time they get to the bottom, they're like, this is really boring. Like, it's always the same thing. When we're adding, it's always the same thing. When we're subtracting, it's always the same thing. I do this type of activity over and over, every time we hit something new that's got like terms in it. Because I want them to continue to see the connection through the entire book that addition and subtraction require like terms, period. That's it. That's the only schemata I want them to have for that. Okay? I do a lot of these matchup activities, and they're very carefully structured for a reason. There are only 4 possible answers that they'll get out, and then there's a none of these. The answers that they get out are often very similar looking, like this is 9x squared y cubed, this is negative 9x to the 4th over y cubed. So they both have a 9 in them, they both have x terms and y terms in them, but they're structured slightly differently. Now, a couple of these problems will come out close to these, but not exactly. So a couple of them will come out like positive 9x to the fourth over y cubed. And our students are so quick to jump at answers that look close enough, you know what I mean? So they do so poorly on multiple choice tests. So one, it's helping them to study. If they do need to eventually take multiple choice tests, they're getting better at coming up with answers that are exactly right on. But also those students who are like on the higher end, who are like, yeah, I can do these problems. I can do these problems, like they know everything, right? They're the ones who always miss these. They always have this little pattern of wrong answers in the grid because they were so sure that x squared y cubed with 9 in front was the same as x squared y cubed over 9. And so they jump at the answer even though it's not the right answer. So these are designed to help them practice with. This is one that's right after you learn negative exponents. So there's a lot of work here with negative exponents and how they get rearranged, and negatives in the problems, which they always mix up, negatives in the problems with negatives in the exponents, things like that. So these are activities we do in class. This is one of my favorite types of activities. This is called mathematical heteronyms. And so they are, in English, that's words that are spelled the same but have different pronunciations and different definitions. And I think to our students, these kind of look the same to them. Like if you look at the second line here, 2 minus 5, 2 times negative 5, 2 to the negative fifth, they all involve a 2 and a 5, right? And I'm quite sure that a lot of our students, they just see a 2 and a 5 and they do something to it. Whatever is the strongest schema they've got in their head. And so this forces them to look at the minutia of the detail and try to figure out what's different. Here's another example about this belief that somehow everything factors, right? I mean, very few polynomials actually factor. And so I want them to encounter problems. I want them to very carefully look at all the terms of the problems and not just, the ones that make the middle number. So I'm trying to force them into that. I'm giving them examples where one doesn't factor and the other two do. They better find the one that doesn't. And so they have to pay attention to things like, well, does it actually make the last term? Did it actually make that middle term, right? And so again, these are problems we do in class, and I've always tried to write these activities. You might think they're kind of strange at times, but I've always tried to write them so that they're easy for the instructor to walk around and grade it, not grade, but tell people whether they're on track. Like all I have to do here is kind of memorize a pattern of where prime is on the page, right? I mean, I might say prime, 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 prime. Okay, I can walk around the room now. And I can help people as I go because all I have to do is remember where the primes are and they'll work out the rest, right? Same thing with this type of activity. All I have to do is remember a line at a time, walk around the room, check that. Look at another line, walk around the room, check that. It's much easier to remember A, C, D, B than it is to remember actual math on each line. So if they ever seem strange to you, they're designed to be that way, to be easy for the instructor to walk around and help with. So at some point I made the mistake of opening up my mouth at a textbook focus group. I've been making these activities for a while. And I opened up my mouth at a textbook focus group and I said, somebody should really write a resource for the classroom so that people have these kinds of activities to work with in the classroom. I think that they're incredibly time-consuming to write yourself. They take a lot of thought. You have to think about, what kinds of things are students doing that we need to encounter, and how do I make that into an activity? And so I thought, well, that would take a lot of time. And so Charlie says, okay, let's write it.
Great idea.
So at that point, I found myself writing a lot of activities for stuff I had no activities for. And at some point, this collection is now up to about 450 activities, plus another 550 pages of other materials, which we'll talk about. So there's more activities in here. There's things like making sure students understand what exponents really mean. Do you understand which part is repeating? Like, for example, students, they either say this is 2 being to the 5th power with the a, right? They very rarely get the opportunity to write out 2 times a times a times a. It's the kind of thing that if it's in a textbook, they won't do the problem. They'll just look at the back, write it down. Right? They don't get anything from it. So, but if you can get them to do it in class, then you can reinforce, do they understand or not? Something like writing this out as negative 2/3 times negative 2/3. Do you understand the negatives in the square? These are the things we want to be checking. So I wrote all sorts of activities, some of them more bizarre than others. This is monomial addition and multiplication tables. Something I've never actually seen done with monomials, but we do all the time in elementary school, just, whole numbers. So I thought, they might really understand this concept of addition versus multiplication if they could see that some terms can't be added. Right, so as we go through and we do monomial addition tables, you can only add like terms, and anything that's not like, you can't add together, right? So they work through some on their own, and they work through some multiplication. Of course, multiplication, you can do all of them, right? There's no need for like units for multiplication, only for addition. And then as a challenge to those students who are just going to whip through it, I always try to write the activities so that the students who are just learning it for the first time will get through plenty of problems, but the students who are, kind of the higher level students will have something to challenge them towards the end. So the challenge here is now, all right, here's a partially filled grid. You figure out what the top lines and the side lines need to be. You work through it like a puzzle, like a Sudoku type thing. Okay. These are expressions all written in triples, and this is designed to show them that, you know how they all think that x minus 2 is the same as 2 minus x, that kind of thing? I want them to see that in some cases it doesn't matter when we change the order, in some cases it does. So for example, these will come out the same, x plus 3 times x minus 5, those are the same. But if I switch the signs, that's not the same, right? And I want them to really focus on learning those types of things. Okay, so anyways, there's all sorts of activities in here, and some of them are quite fun. This is an activity on the Pythagorean theorem. They have to work out all the pieces that are missing on the boat. There's a trick to it. You start with A, and you work your way up through the alphabet, and it'll go quite nicely that way. But it's different than things they've seen before. It's a lot of work with categorization, so trying to decide, not do the whole problem, but decide what kind of problem it is. So again, trying to get the schemata to form well, so they know which script to execute. So this is a problem that specifically just choose the case. What type of problem is it? If they can choose the type of problem, then maybe they stand some hope of running the right script. If they can't choose the type of problem, they can't get out of that. Again, another type of activity of classification. All I want you to do is tell me what type of factoring I should run. And then maybe the first step of that. But not run the whole problem, just that part. Great things for discussion in class. So at some point here, this was finished. Again, there's more stuff in here, which we'll talk about in a second. It was, I like to think of it as baby. It was 11 pounds, 1 ounce. And if you've never written a textbook, I just want you to know that it's not an easy thing, and that's what my office looked like when that was done. Right? Textbooks, they come to you nicely formed, all the blood's been cleaned up off of them, and everything like that. But that's what it looked like when mine was done, and that's what my office normally looks like. So you can see that, well, maybe now this is not really normal, but you can see that there's a big difference there, okay? You have to remember that behind every one of these projects, there is somebody going through that, okay? I could not drive for many weeks while I was working on this because I kept getting speeding tickets because I was thinking too much about the algebra and not about the driving part. So let's move on to problem number 2. So problem number 1 was the students' fragmented conceptions and how can we try to bring those together. Problem number 2 is that math instructors tend to be oriented towards, this is just a fancy way of saying lecture, we tend to be oriented towards lecture. It's information transfer, teacher-focused learning. It's a phrase that's used in educational circles. And about the CBMS studies show that about 85% of us lecture. So, and there's a variety of reasons for that, but some recent research I've been conducting shows that it tends to be because of content. There's so much content we have to teach. We feel like there's little time to get outside of that. So I really wanted to try to start dealing with this problem of lecturing because I think that we end up with 2 situations. We have to teach both ends of the room, the low-end student and the high-end student, right? So if you teach the low-end student, the high-end student gets bored. If you teach the high-end student, the low-end student gets frustrated. And if you balance this perfectly, then everybody's mad at you. Have you found that? I mean, it's a really difficult thing. I mean, it is really hard to teach algebra. Well, at some point I began recording all of my lectures for algebra, some of it live in the classroom, some of it outside of the classroom, and I had this realization. I realized that all we're doing when we lecture in the classroom is duplicating what can be done by a video. Now, at some point, there are these great videos out there. There's the Rena Petraea videos. I cannot ever look like that, so I will never be able to live up to that. At some point somebody will publish the bikini algebra videos, in which case, you would not be able to compete with that kind of thing. But, even in all seriousness, the government and the Bill Gates Foundation is in the process right now of finding the best lecturers in the country to record the best set of lessons for all of the math courses courses, all the developmental math courses, and they're going to put it out freely and openly on the internet. So you have to ask yourself this question: when that happens, if that's what we're doing in the classroom, why do we need instructors in the classroom? To talk back and forth? Okay, now another interesting thing is that, so you say, okay, well, but during, and I said this too, I had this argument many years ago with somebody. I said, but, you know, when I'm lecturing, I'm asking questions of the class, right? And they're responding. Well, the research actually shows that our interpretation of that is different than what actually happens. If you actually, like, make a chart, have somebody do this if you don't believe me. It's really interesting. Vilma Mesa at the University of Michigan is doing this research, and she maps out the classroom. She puts a little point for every body in the room. And then she has somebody observe the class. And every time the instructor asks the question, she makes a mark for the instructor. Is it a rhetorical question, or do they actually expect an answer? And then every time a student answers, she puts a mark above their heads, right? It turns out that this very fluid conversation we think we're having with the class is actually a conversation that we're having with 2 to 3 students. Not the class. 2 to 3 students. Well, that also can be mimicked by a video. When I record mine live in the classroom, I'm getting those questions in the video too. And since the majority student experience is listening to somebody else ask the question and listening to the answer, that is, I'm afraid, duplicated by that video. The only person it's different for is those 2 or 3 students that actually engage you with the material. So the biggest difference that needs to happen here is that rather than the conversation all being between me and them, it might be a good conversation, but it's still a conversation that's happening like this, right? What we need is the conversation to be between students, because that can only happen live in the classroom. It needs to be one where the students are working and we're going around and targeting those specific problem areas, because that can't easily be replaced. That absolutely needs to be what happens in the classroom. So that's what I did. I started having students, you know, they were already doing all these activities. I started to have them do activities with each other. I mean, they were already doing activities with each other. I started to have them very actively doing activities in the classroom. Some of you guys have the binder here, so you can take a look at that. But that's basically what it looks like. You can make copies of the pages. And so what I do, kind of instead of, you know, like a one long lecture, I talk for maybe 5 minutes, and I say, okay, let's do an activity. I want them to do the work. I know I can do the work. They know I can do the work. And we all know that them watching me do the work is very little for them. So they need to be the ones doing the work. So this is what my classes look like now. And this is called concept-centered, student-focused teaching, where the students are the ones teaching each other. The students are the ones interacting with each other. I am there as a facilitator. I'm there to get the problem started, but that's what the classes look like. And you can see them talking to each other. They look at each other's work. They argue with each other. There are a few dysfunctional pairs. They sometimes almost come to blows. Kind of kidding. But, you know, we have this one pair in the classroom that we call Beavis and Butthead, because they really are quite the pair. They think it's funny. They purposely argue with each other now. So you can see that this is a very different look to it than what we're used to seeing in the classroom. It's basically students teaching students. I'm there, and the beauty of doing it on boards, and so I do a lot of my activities now. I have them go up to the board with their worksheet and work through problems. I can stand on one end of the room and see all the work that's happening around the whole room. Okay? And that means that I can, you know, either call out names and say, oh, back up a step, look at that, you know, or I can walk around and just coach them and try and help them to see where their differences are. I always try to challenge them with a problem that's a little bit harder or that actually uses a different schema. You know, like, so after, this is a calculus example, but after we do U substitutions, they want to U substitute everything. Right? They're so sure everything involves a U substitution. So I'll have them do 2 U substitution problems, and the third problem I throw at them will involve no U substitution whatsoever. So what do they all do? U equals, DU equals, and then they all stand and look confused for a while. But that's good, because I want that experience to happen. That's exactly what I want to happen in the classroom. I want them to take that schema they just learned and separate it from I don't want them to write it over. I want them to move it into a different category and go, oh, right, we can still do problems that way too. And so we need to have these challenges in the classroom. Yes?
So what happens when you have that student that just refuses to go to the board? What do you do with them?
I tell them that they can go home and watch the videos at home if they don't want to participate. It hasn't happened. The other thing I do is I say, okay, you are now the recorder for the whole class. I turn my computer around, I make it into a tablet, I turn on the recorder, and I say, there, you may sit there, you're making the problem for the rest of the class. And we have a recording of it. So, I mean, there are ways to entice them to make it less desirable to sit down than to stand up. But the other argument they give me is, but I want to be able to take my notes home, right? Which is a valid argument. And I say, oh, wait, what's that in your pocket? What is that thing? Oh, it's a cell phone. And what does it have on it? Camera. Click. There, you have your notes. You can take them home with you. If you have a smart board, you can just rotate one of the pairs through the smart board. And the smart board will create a complete recording of, what you did in the classroom. So there's lots of ways you can do it. You can take a picture of the problems yourself to post. But the point is that when you get them out of, when you ask them to do a problem at their seats, what usually happens?
They sit there and wait.
They just sit there and wait. They wait for what? They wait for you to do the problem. They don't want anything wrong in their notes, right? There's something magical about whiteboards. They stand up out of their seats. They don't want to be the only ones not writing. So they start to write. And because you can so easily erase, they're okay with it. They're okay with erasing. I don't know what it is, but they just seem to think better when you pull them out of their seats and throw them up at the boards. I think the trick is how you start it. You don't tell them up front it's going to happen. You just say, okay, everybody stand up. And everybody stands up. You say, walk to a wall where there's a board. Any wall. Just walk to one of the walls where there's a board. When they get there, you say, find a partner. Somebody standing next to you. Introduce yourself. And they're still kind of thinking, what the heck is going on? But because you never warned them what was about to happen, you get them doing it. And I've done this at math conferences. I've got instructors to pretend the walls are bored because they have no idea what's happening until they get there, and then they're pretending to write on the boards and all sorts of stuff. But our students, you get a little bit, just a tiny bit of pushback from one or two students, and then all you have to do to fix that is have a lecture day one day. Like, actually walk in and lecture for the entire time, and I promise nobody will complain at any point after that. I mean, by the end of class, they'll just be like, drool coming out of their mouths, and they're like, seriously, you're really going to lecture the whole day? Okay, we'll go to the boards from now on. The other trick I should tell you is that a way to keep this from becoming dysfunctional, I have one person write, the other person help, okay? And then every two problems, so then they switch to the second problem, and every two problems, then one person moves to the next group. So it's a constantly rotating group of people. You're always working with different people, which means the pairs are only ever dysfunctional for two problems. So if they're dysfunctional, it doesn't stay for long. And if there's one student that everybody just kind of doesn't like to work with, because they have an odd personality or something, everybody knows they're not going to be stuck with that student for more than two problems, and it's fine. Okay? Yeah?
Do you have time constraints?
No. I have no time constraints, because what's happened is the examples that I normally do, they do now.
But do they do in the time that you have?
Yeah. I mean, it's really just, it's interesting. I mean, if I would normally have done 8 problems, I might do 7 now, right? I do 1, then they do 6. But because they're doing it themselves, you'd be surprised how quickly it goes, because they actually understand as they go. If you have to teach like a 3-hour class or a 4-hour class, this is like invaluable to just have them stand up and do problems. So the third problem of algebra that I think we should talk about is this one. It's kind of our dirty little math closet secret. We have a huge population of adjunct instructors, right? In my own personal story, when I taught my very first beginning algebra class, I had 48-hour notice. I went from being a run-of-the-mill person to an algebra teacher in 48 hours, right? That was my prep. I was handed a textbook and, given this, well, good luck, And that was about it. At 2-year colleges in particular, part-time faculty are teaching 44% of the math courses. And they make up 65% of the faculty because they teach such a disproportionate number. 44% of our courses, right? And many of those people are just being handed a book and told good luck. Now, some of them we're lucky to get. They're from the high schools, they taught for years, they have experience, and that experience and expertise is really valuable. And it's something that ideally, we would say every new math instructor gets a mentor, and that mentor would work closely with those instructors and really make sure they understood what they were up against and these ideas that students struggle with and things like that. So I thought that this should be the case. I thought that every instructor should get a mentor if they want one. And so one of the things I wrote into this resource was things like instructor tips, and this is as big as I can get it. So I'm just going to read you the first little part of this. Natural instincts lead students to believe that x to the 0 should be 0, although it's not. We see this all the time. This is an unfortunate remnant of their learning the multiplication property of 0. Since we first learned that any number times 0 is 0, we begin to associate any expression with a 0 that involves multiplication with the answer of 0. We see this with students with like e to the 0 too. They're just absolutely sure e to the 0 is 0, right? And so these types of things are written into the teaching guides in this binder, so that new instructors who really have no idea what to do start out by getting some tips about what to expect out of those students they're about to see for the first time, and how they might combat the issues that those students have. I try to show them things like, why is it so important that you see in a lot of problems, write your answer without negative exponents. Why is that so important to write the answers without negative exponents? Well, it's two reasons. One is that it's very difficult for us mentally to process a number with a negative exponent because we're so used to processing numbers with positive exponents. But the other reason is that at higher levels, students have to be able to flawlessly look at a problem and get it without the negative exponent because they can't, or move it with a negative exponent. They can't do the math without doing that. So like a calculus problem like this needs to be rewritten like this. So I'm trying to give them examples of what might come down the road that will also help them to understand the context of what they've got in that problem. We talk about things like, why is it so difficult for students to understand the difference between the different ways of writing functions, how these common schema that are activated wrong, like what those are and how they might work with those. So basically it's trying to act as a mentor to any instructor that wants to take the time to read it. And all of these new instructors we have, I think, well, I wish somebody had told me all this. This took me years to come up with some of these explanations for what was happening. Or having conversations with more experienced teachers. And with the number of instructors we have just walking in, I think they need that. I think we need to provide it to them. I think it's only fair. There's a Malcolm Gladwell book called Outliers where he talks about to become an expert, to become truly an expert at something takes 10,000 hours. 10,000 hours. I'm not there yet. I counted up like the number of hours I've taught algebra or thought about teaching algebra or tutored algebra. I'm at about 8,000 hours, right? So think about that versus walking into a classroom with 48 hours notice. There's a huge difference there. The other thing that's in here are teaching guides for each of the sections, and these basically just tell you kind of the context of where to put activities that are in the book, so like this activity would be a good starter, this activity would be a good follow-up, that kind of thing. It also gives them more examples that are worked out so that they can show some more examples in their classes. So for every section, there's examples here, and there's always more than you need, so that you can kind of choose the ones that you want to have. So if you just need more examples to show, again, these are people who are adjunct instructors, especially, they're pressed for time. Some of them are teaching for 3 or 4 colleges. It's just, we need to provide them with resources. So the teaching guides are also there as a resource. There's also some assessments built into the binder. So I know everybody as administrators likes to hear the word assessment, right? It's like there was a drinking game at faculty seminar days. It would have the word assessment in it. So so we talk about things like metacognitive skills, which is the ability to know how well you know something, right? So I ask students, there's activities in here that allows them to think about things like, how well do I, before I study for the test, how well do I know these topics? Rate it. On a scale from 1 to 5. 5 is most confident, 1 is I don't know how to do these problems. Right? Because they tend to study the things they already know well, because that's what they like to study, right? We tend to not study the things we do poorly. It's the same with real life. We tend to do the activities we do well, and not do the activities we do poorly, right? So we need to recognize that and have them go through, rate, before I study, how do I feel about these topics? And then actually work on improving the ones they're poor at. So, this is my scale, and basically this is my teacher speak, and this is my, what it says in the book, but, that's down at the bottom here. I think I should have attended more class, right? We see that a lot, so that's a rating of 2. I also ask them to look at big picture ideas, again, making sure they can bring up the appropriate different schema they have in their heads. So it's kind of like a practice test, only they don't work out the problems. They think about how to work out the problems. And this is a great one to do in class, like on a review, because basically you're just asking them to tell you what kind of problem it is. Like, what's the name of this problem? What kind of a problem is it? Is it an inequality problem? Is it an absolute value problem? Is it, what is it? And then how would you start the problem? Because there's so many students that just blank, right? If they could draw the appropriate schema, they could do the rest, but they can't draw it, so we need to have them practice for that particular step, knowing the difference between problems. So this is all available in this binder that these two guys have already snagged here. It's exactly 1,000 pages, so it's a lot of stuff in there, okay? But you can make copies of the activities for your classes. It's copyrighted that way. And if you find yourself making a bazillion copies and you've broken your department's budget, there's also workbooks with all the activities in them. So you can just have your students purchase the workbooks, and then you can use as many activities as you like without any trouble for making the copies. Okay, so the fourth problem of algebra that I think we need to talk about, which none of you mentioned, but I think it may be a bit of a shock to you. I'm not sure. We'll see. Computer algebra systems. I'll let you read the cartoon in a second. So computer algebra systems, they've been around for about 20 years now. Derive was the first one. We have them on TA9s, we have them in Maple, Mathematica. But there's always been a cost barrier to using these, so it hasn't been too much of a problem. We've been able to kind of just ignore it as a problem. Every once in a while there's a little skirmish, a math war about it, but for the most part we just say it costs too much, we're not going to worry about it. But now, today, as of May 15th of last year, we have CAS, and it's on any computer with internet. And it's available for free on any computer with internet. Jill's going to start passing out handouts, so I want to make sure you get those before you go. So I want you to stand up if you've heard of Wolfram Alpha. Stand up if you've heard of Wolfram Alpha. And stay standing if you actually went and tried Wolfram Alpha. And stay standing if you thought about ways to use Wolfram Alpha in your classroom. And stay standing if you've used Wolfram Alpha with your class. Good job, Rochelle! She's been to 3 of these presentations, so I think she knows by now that she's supposed to have done this. Alright, so I'm going to show you what Wolfram Alpha is, because you have to know this exists, and we have to start thinking about how we're going to adjust. Okay? It's basically like Google. You type your request in, and it spits out everything it can find on the top of it. So you can literally type in line, and give it 2 points, and here's what it gives you in return. It gives you a graph of the line. That's not so bad, that's okay. It gives you the equation for the line, the x-intercept, the y-intercept, the slope, and the distance between the 2 points. That's its normal output. Everything it can find. You can do strange things like give it lists of objects, any objects, cities, names, chemicals, and if it has any data on those objects, it will give you a comparison between them. Right? So whatever you put in is separated by a comma, you can get this out. So we can put in things like trigonometry stuff, like triangle with 3 sides, give it 3 sides, and we get a beautiful graph of what that triangle looks like. You're thinking, yeah, that's not too bad. But also the area, perimeter, and all the angles of that triangle. So it's just solved the triangle. I don't know about you, but I remember taking trigonometry and spending hours solving triangles. And all of a sudden, I don't want to do that anymore. I just want to do this. Because I know it'll be right, and it'll save a lot of time. You can put in a function. So here's negative x squared plus 4, and it gives you a couple different graphs. It usually tries to show you kind of the middle of the function where the important stuff happens, and then some kind of graph that shows you the end behavior. It's kind of standard default. It tells you what kind of figure it is. It shows you factored forms. It shows you roots. It shows you the derivative, the integral. If it has a maximum or minimum, it gives you that. If it has an area that's bounded under the curve, or that's between the curve and the x-axis, it'll find that for you. And, oh, did I mention this? You see that? There. It'll also show you the steps. It'll show you the steps for solving equations. It'll show you the steps for finding derivatives and integrals. Anything it's been programmed for, it will show you the steps for it. So even if you're thinking, well, this doesn't apply to me, I assign all my homework by hand. It shows the steps. Okay? Every computer with internet access. If any of you have phones with internet access, you can use it on your phones too. It runs off the internet. Okay? So here's some things that you can be doing with this. I mean, if it seems kind of scary, first of all, it should. It should be a little bit of a shock. If you've never seen it before, you need to go play with it. You need to know what's out there. Because one, it is a little scary. That means we need to change some of the things we do. We need to stop focusing so much on the minutia of problems and focus more on that general, do I understand what kind of procedure to use? Do I understand how to find the patterns in the problem? Do I understand what the logic is behind this problem? Not, can I actually factor this 5-term polynomial? Because if I had to factor a 5-term polynomial, I would now go here and just type it in. And once you start to feel that way too, you have to change the way you do in your class because you just can't stand teaching it anymore. Okay? So here's some of the things that make this really cool. At the top of the page, I don't think I have a page top here, but at the top of the page, when you do a search, there's basically a hyperlink for that search. Like this is the search x squared plus 4, basically, or negative x squared plus 4. So if you just take the hyperlink at the top of the page after you do the search, you can just paste that hyperlink into a chat window, into a discussion board, into an email, and whoever clicks on the link will pull up the exact same search you were just looking at. So it's instantly shareable. So whatever you just saw, you can share with somebody else, whether you're on Facebook, or whether you're in a chat window, or a discussion board, whatever. You can, in your course shell, you can say, click here, and put the URL behind that if you want to show the graph of something. So you don't have to draw the whole graph and put it in there. You can just say, click here, and send students to see it. Of course, that means your students will see it. There'll be no hiding from Wolfram Alpha after that point, because you'll have shown it to them. But that's maybe not such a bad thing, because it also does things like this. If you right-click on any of the images or equations in Wolfram Alpha, you can hit Copy Image, and then you can go to your test, assignment, or whatever you're having the students turn in, and hit Paste. And so that image is now in your assignment. It's just a simple copy-paste. It has never been easier to get graphs and all sorts of equations and the steps for equations, things like that into your assignments. My students are already just super good at this. My calculus students, they pull in all of their graphs from Wolfram Alpha. And they use, paint programs. If they need a shade, they pull in the graph and then they shade the part they need to shade and paste it in. I mean, there's no complaints anymore about having to get graphs or even the equations because they can copy the equation. They can just type the equation and copy it if they want it really nicely. So, we have to think about, really, we have to think about what we're going to do with this. And I want to just show you, first, how much time do I have left?
About 5 minutes.
5 minutes, okay. So I'm not going to ask you that. I'm just going to show you one of my ideas of using this, and that is to use it as an inquiry-based learning tool. Okay? Kind of thinking along the same lines as these activities. I think now I have to write a set of activities that use Wolfram Alpha. Shh, don't listen to that. But I think that there needs to be a set of activities now for using Wolfram Alpha as an inquiry-based learning thing. Hopefully he was not paying attention when I said that. You were like, So what I have students do now is this type of thing. I give them 20 problems. This is before I teach factoring techniques. I give them, and I haven't actually used this when I did it with calculus in a different version, but it's the same idea. So you give them 20 problems for factoring, and you actually tell them to go to Wolfram Alpha, type in factor, and type in the expression. And it will very nicely give them a factor form. Right? So you tell them this. This means you are opening up Pandora's box. It'll keep you honest for the rest of the semester, let me tell you. So you have them write down the factor forms. They don't know what they are, but they're writing them down. Okay? And maybe they know what they are a little bit because they could multiply them out and see that they really do work. You could have that be a third column if you want. Multiply them out and verify they're right. But what I want them to do with this is then after this, I have them cut these apart into little slips like portions from fortune cookie. And I say, all right, I want you to take all of these little slips and put them into piles based on the type of answer you see. So find commonalities amongst the answers. So some of the answers are going to look like binomial squares. And some of the answers are going to be like x plus a number, x minus a number. They start to see that those answers have kind of come up commonly, and they put them into piles based on the answers. And then I ask them to write statements that tell me why those piles are similar. So to look at the expressions that got those answers and say, well, what from those expressions gives me these, these answers? So they actually make statements and they support them with their own information that say, okay, this grouping I have here, the group 1, 2, 5, and 7, they all have answers that are like x plus a number, x minus a number. And they say this in their own words, and that's fine because I want them to develop these schema in their heads for themselves. And then I ask them to provide, some examples of them, and then tell me what's similar about the problems that might cause the answers to be that way. So before I've ever talked about factoring techniques, they already understand that there are different factoring techniques, and they are cued by different kinds of problems, right? And it's really fun to grade stuff like this because you really see that students can think. And it makes you very happy. At least it makes me very happy. So, should we be changing the content of algebra because of this? I think probably we should, but it's not going to be pretty. We've had math wars before. I'm afraid, it's just never pretty. There's the traditionalists on one side and the kind of modernists on the other side, just arguing from two completely different standpoints, unable to see the other side of things. I think it's going to be a mess, to be quite honest. But should we be thinking about this? Absolutely, we should be thinking about this. Because it's our opportunity to focus on logic and patterns and things like that instead of fine details. If I really want to do a problem correctly, I would just go to work now. I would not work at my hand because it's going to be fast and it's going to be easy and it's going to be right. Should we change the way we teach in the classroom? I think we better change the way we teach in the classroom. We have seen industry after industry get outsourced in this country recently. Most recently, the whole journalism industry, right? Newspapers have gone through a total upheaval. If we think that education can't do that, we're wrong. It's already happening in little pockets all over the country where labs are being created where the lab teaches students math. They're all funneled into the lab, there's one person for 600 students, and that person is just in charge of making sure they process correctly. That's not what math teaching is about. It should be about encountering patterns and logic and making connections and fixing faulty schema. We don't do enough of that in the classroom, and we need absolutely to do it and spread it. So I'm going to come back to my first image here, that I think what algebra really is not necessarily a way to eventually get to doing application problems or anything else. I think it's a very beautiful subject that teaches logic, that teaches pattern skills, and I think we're losing that because we're not focusing on those things. It's something that works out in the minds of our students. And you think about the kinds of subjects that require algebra, some of them really do need algebra, and sometimes we just want our students to be good thinkers. And that's what algebra is supposed to be doing, not really teaching them how to factor difficult things, but become good thinkers. And so we need to focus that. I would also like to give a shout out to my fantastic illustrator, Matt, who is the best algebra illustrator ever, although he'll claim now that there is nothing funny about algebra after making 100 cartoons for the book. And I'll just leave it at that. You can actually download some of the activities from the community site for this, and print them and try them out in your own classes. And that's it. I'll take questions if you have any.